announcements also. You got this bag with this some information about internet, restaurants, where to go for lunch, and some other information about the local infrastructure. You can also use downstairs. We have a room full of tables that you, on the first floor that you can use to work. Because the idea of this workshop is also to be light. So you probably saw from the program that there are not many talks scheduled, so you have time to work and discuss, and that's the important part of this workshop. It can be even lighter today because some of the speakers have not arrived yet. So we'll see what happens. It can be really light, and then you have plenty of time to work, which is. So Ivone has not arrived, and Ronaldo has not arrived. So two people that have not arrived. Jay has a lot of time. We can grill Jay. Huh? So we move. Veselin agreed to move if Ivone and Ronaldo they do not arrive. So the idea is to move Veselin up, and then we end the day. So we have discussions. Okay. So that's the idea. See how it goes. What? What is? Oh, this is wrong. Okay. This is obviously wrong. Okay, so it's a pleasure to have Professor Jay Hubisz from Syracuse University, and he's going to talk about brane world. So today is mostly cosmology, so he's going to talk about brane world cosmology from symmetry principles. So Jay, let me just put full screen, okay?
Yep, very good. Okay, thank you so much for the introduction and also for the hospitality and welcome. I'm looking forward both to this workshop and then another week of good physics here in Sao Paulo. So what I was happy to get this invitation, and for this workshop in cosmology, because it's a rare time in my career when I'm actually working directly on something directly related to cosmology. So this is work that is in progress right now, and so I don't have the final conclusions for this endeavor, but I hope to present the formalism that we're trying to approach and motivate the importance of what it is that we're trying to do.
Like the e to the I pi. That is multiplicating where right
What?
e to the I pi times the value expectation. That should be this one.
Yes. I can't even get past slide 0 with Carlos. And I would like to say I'd like to dedicate this talk to the memory of Eduardo, who I think would have really enjoyed this talk. This is related to things that I have discussed with him over the years, and so he's sitting somewhere in back looking on, although he won't be able to ask me any questions, unfortunately. Okay. So just the very broad motivation for where we're going here is that we all are aware of the fact that extra dimensions, both large and small, have over the course of the last couple decades and more proven to be sort of rich troves for model building and phenomenology. They offer kind of new perspectives on the Higgs hierarchy problem, interesting ways to think about the flavor problem and hierarchies of fermion masses, very interesting ways to think about different mechanisms by which you might break supersymmetry to obtain a low energy theory without it. And interestingly, new viewpoints on the cosmological constant problem. I am going to start out this talk by looking at a couple of specific examples that have come out over the last couple of decades where there are very intriguing cosmological behaviors of brane worlds in the presence of certain types of instabilities where the system does not want to be static, the system actually wants to move, and thus there is an actual cosmology that is part of these brane world scenarios. The two examples that I'll discuss as motivation are the following. There are examples where, in a couple of different models, where you can obtain cosmologies that look like, from the perspective of some localized observer, some guy that's stuck on a brane, looking at his or her universe. This person on the left here, where the universe that observer sees is looks like it contains matter and or radiation, but there isn't actually any matter or radiation in the picture. As I'll point out, this behavior is intrinsically tied when there is a relativistic motion of the branes in these scenarios. So the two models that I'll focus on are first the RS two-brane model, where there are tensions that are mistuned. That is, usually there's a relationship between bulk cosmological constant and tensions on two branes in this construction, and unless you fine-tune them to fantastic accuracy, the system wants to move, the branes want to collapse or fly apart from each other. And this is a famous issue with early Randall syndrome that was then later solved by Goldberger-Wise stabilization. But what is interesting is that the solutions, when you relax the tuning, they involve not just lambda-type cosmologies, not just cosmologies with vacuum energy, but there's a radiation component to the effective Hubble expansion that brane-localized observers see. And I believe the first to point this out were these folks here, and the rho lambda cosmologies, I think, were first explored in detail by Caliper. But there were very many papers on this subject, and so there's a trove of nice studies of these models. Another very interesting one was this story that came from bosonic string theory, where Ashok Sen was looking at the dynamics of brane, anti-brane pairs, where there is a tachyon in the system that is signaling the instability or the tendency of the system to want to annihilate the branes. And what comes out of this, if you look at the effective theory for these branes, is that as the tachyon rolls down from its unstable point at the top of its potential, the effective stress-energy tensor on one of the branes evolves from one that looks like a lambda-dominated cosmology to one that is matter-dominated. Okay. And so I'll start in reverse order, taking a look at at the effective theory that Sen wrote down for these annihilating branes. The effective theory for the tachyon, and I missed a couple of minus signs here. There should be a one in here and one in here. That the effective those come later. And now what happens in this picture is this potential is a tachyonic potential, so it's upside down, and phi wants to roll down the potential, and phi is effectively the inverse separation of two branes, as I'll show in the picture on the next slide. And so what happens is the tachyon rolls, but now, because this is a theory of branes, as the tachyon rolls, the inverse brane separation, the brane can't move faster than the speed of light. And so the tachyon hits a sort of a speed limit as it's rolling down the potential. It's not like a Hubble friction term, it's something different that's saying that the brane just can't move faster than the speed of light in the space-time in which it is embedded.
Sorry, I don't understand the kinetic term that's inside the determinant.
Right. So if you expand this out to lowest order in derivatives, there will be a standard kinetic term for the tachyon that comes out of this.
So it's canonically normalized.
Well, not quite, because there's a v of phi out in front, so it's not fully canonically normalized in this.
So you can perform a field redefinition and canonically normalize it, right?
I don't think you can't get rid of all of the higher derivative terms, though. You can canonically normalize this, so the leading order derivative term has the standard 1/2 d mu phi squared, but you can't eliminate all of the higher derivative terms in using that same field redefinition. So the physics of the speed limit is still encoded after performing such a field redefinition.
Okay. And one more question. Sorry, go ahead.
No, I was wondering the natural units is the Planck mass, or what is in front of theta?
Yeah, that's right. There's some squiggles out there. Yes, the Planck scale is presumably what's setting the scales here. This is coming from string theory. So.
How about gravity? Are you working in Einstein? Jordan frame at this point, or it doesn't matter?
I'm honestly not sure. So there's no gravity in this picture here. This is the effective theory after integrating out all of the gravity fluctuations and all of the string modes, things like this. No. There's a effective theory for the motion of the two branes. This tachyon is going to involve the metric fluctuations in some way. There's open string modes being exchanged between the brane. There's all this stuff. I don't want to focus on exactly how we get this action. That's not what I want to draw attention to. All I want to draw attention to is that if you follow the procedure that Sen told us to follow and you write down this effective potential, the behavior that you get is the following. As these branes are collapsing in towards each other and the tachyon rolls, it hits a speed limit as it's moving down. And if you are living on one of these, on the brane, then there's an effective stress energy tensor that you can calculate by just varying that action with respect to the metric. And the T00 component looks like this, and the Tij component looks like this. So as the tachyon rolls and it's picking up speed, and it asymptotically approaches its speed limit, if energy is conserved, which it must be in this case, then the pressure here, as phi dot approaches 1, the pressure is going to drop down to 0. So as the tachyon starts from the top, it evolves from a vacuum energy looking like like stress energy tensor down towards one that looks like one that is non-relativistic matter. And of course, eventually the branes annihilate, but that's not in the context of this EFT. Once the branes are within sort of an inverse Planck length of each other, you cannot apply this formalism. Just an order of magnitude. That's roughly what the tachyon corresponds to as the brane separation.
So, but in any fixed order in the derivative of phi, I'm not going to see this, right?
That's right. Yeah. No, you really need all of the higher derivative terms, and that's crucial.
Why do you call it the EFT, right?
Because the local, if I try to bend the brane a lot and get high local curvature, that'll go outside the realm of this effective field theory. So you can't have very curvy and bunched branes in order for this EFT to apply.
And where does this curvature enter the action, the curvature of the brane?
Where does the curvature of the brane enter? So there are higher order terms that you can add in the EFT, and those are, if you like, higher derivatives that you can add that will be encode the extrinsic curvature and things like this that you can couple stuff to. Okay, and that's all I wanted to say about this. This is an interesting brane scenario, and out of it, without putting in any non-relativistic matter, you get out cosmology that looks like non-relativistic matter. And there was a string of tachyon cosmology papers that were focused around this EFT in the early 2000s. Okay, so that's the story that Sen was telling us order 20 years ago. And now I'll talk a bit more about something that I've worked on directly, and that's these Randall-Sundrum two-brane scenarios, where you have a bulk cosmological constant, lambda 5, and it's in terms of it's proportional to a curvature k squared, where this gives us anti-de Sitter space if lambda 5 is a negative cosmological constant. And now this system is truncated on the left on the right by two branes, and these two branes have tensions T0 and T1 respectively. And when we write down this solution to Einstein's equations, we've made the presumption that the metric itself is static, that is, there's no time dependence in this metric. And what you will find is that that metric is only consistent with the sorry, was there a question?
Is your mic on?
I think so. It definitely sounds like it's on to me. And now this metric is only a solution of the Einstein equations if the two tensions are tuned such that this relation exactly holds, that T1 is equal to minus T0 is lambda 5 over K. And this is the ansatz that's necessary to get a cosmology at low energies that is just a flat Minkowski. It's just flat Minkowski space, so a non-dynamical cosmology. Okay. But now one might ask, what happens if I relax that assumption of this tuning? If I relax the ansatz that the metric does not depend on time? And I'll go quickly without deriving everything, but I'll show you the kind of main steps associated with figuring out what exactly are the time dynamics of this system. Well, you can start off with a metric that has an arbitrary function of y and t out front in front of dt squared, and then a function of y and t in front of the spatial three slices. Yep. And then here's our y coordinate. And you can show that you can use the various gauge invariances to reduce the metric to a form where first there is only two independent functions. And then the Einstein equations can simplify this down so that there's only one single function, a evolving scale factor that depends not only on time, but also on the extra dimensional coordinate y. And this has been set up so that if I look at A evaluated on the UV brane, that t here is the proper time that UV brane observer will measure. Okay, so A naught is a scale factor described on the UV brane. So when I say A naught, I don't mean the usual A naught of cosmology. I mean A evaluated on the UV brane. Okay, and then you can continue to turn the crank and work hard to solve Einstein's equations. First, you find that you can solve for the y dependence independently and separate out the t dependence into these two functions, lambda plus and lambda minus, which are purely functions of time. And then you can continue to turn the crank, and you find that there's another relationship between lambda plus and lambda minus. And this is the one that I want to draw attention to, because in the process of relating lambda plus and lambda minus, there is an integration constant, and that integration constant appears here. Okay, and now the last step will be to impose. So now we've basically got everything we need. We can solve for lambda plus using the UV brane metric junction condition, and that gives us lambda minus. And so the bulk geometry is totally determined at that point. And then there's a final consistency relation that says that whatever A of y of t I get here, if I plug in y equal to 0, I better get A naught of y and t. And imposing that consistency relation does for you is it gives you a differential equation for the Hubble expansion evaluated on the UV brane. And so the Hubble expansion at this point is given by just the usual A dot over A squared, and that lambda, which was purely an integration constant in deriving the possible behaviors of the dynamical metric, shows up with a 1 over A naught to the 4, and delta naught here is a measure of the mistuning in the UV brane tension. So if I twist away T naught from its fine-tuned value, then that delta naught differs from 0, and you get a term that looks like a vacuum energy term. So you get a vacuum energy plus radiation. So again, without adding any stuff beyond cosmological constants and tensions, this system of branes has associated with it a Big Bang cosmology.
Sorry, so just to make it clear, so what dimensions are expanding in this scenario? Are
So you.
the y or the brane or x?
So the way that we've written it down, there's a scale factor that depends. An evolving scale factor in A of t that depends on your coordinate y.
Right. So is the y coordinate that's expanding?
Not in the way that we've chosen to parameterize the coordinates here.
Or all
Right.
dimensions are expanding? So this is a 5-dimensional model?
This is a 5-dimensional model.
So
And well, so as we'll see, so I think the question you're asking is what I'm about to talk about next, which is, so I've fixed it so that my y coordinate is, well, that it has this behavior that I've set up here in the metric, that I've declared that that's sort of my ansatz, and I've done some gauge transformations that give me that. And if I perform those gauge transformations, I can't set the position of the IR brane. So if there is cosmological expansion in the 5 coordinate, it will be encoded in the motion of the infrared brane. And so that's the next step. So I think that's what you're asking.
We live in infrared, right?
Right now we're living on the UV, right?
That's
Yeah.
the question. I was
Yeah.
wondering why we normalize it. So UV?
We live on the UV, and you can also do the same thing from the perspective of an infrared brane observer, of course, but we usually live in the UV. You're made of quarks, yes? Quarks are fundamental and usually located towards the UV brane.
But the Higgs is in the infrared.
Well, that's where they go to get their mass. Okay, it'd be very interesting to put matter into the bulk and understand exactly where do we live in this evolving universe. And that would be an interesting thing to try to study, yeah. Okay, so the next step is, so far we've ignored the IR brane, and its motion is going to be determined by matching this metric that we just wrote down onto the brane tension, right? I've got to match the metric onto, there's a brane localized component to Einstein's equations, the zero junction conditions. Now, when you do this, there is a square root factor that encodes this precept that we know that the brane can't move faster than light. So if there was an underlying full action for the radion, including all higher derivative terms, we know that it would give us this factor here like this. And because we're fully solving the geometry, it's not surprising that this appears here. Now, n is just this fact function of a dot and a. And so all of these metric functions here are presumed to be evaluated at the value of y where the IR brane is. So this is some very nasty, although it's only first order, differential equation that you can solve for in principle to extract out the motion of the IR brane in this geometry.
So n is not an infinite.
Sorry? N's not an independent function, it's just I got tired of writing down all the a's, and it was easier to write it down this way, where it just looks, it's more clear that this thing is the derivative with respect to proper time on the infrared brane. Yeah.
N is an integer. So otherwise you call it nu or something that.
And n is a perfectly good letter. Okay, and so I think this aspect actually has not been well studied. What exactly is the infrared brane doing in this construction? And so we started just exploring solutions to this big crappy differential equation that arises from imposing the IR brane junction conditions.
But this R, big capital R, is just a distance?
Yeah, exactly. It's the proper distance because I've put just a minus dy squared between the two branes. So R is the proper distance between the UV and IR branes.
And you want to see if there's a fixed point or something that stabilizes it?
I'm not looking for a fixed point. I'm just looking for what are the cosmologies of this. I've put in this radiation term as an integration constant. If I put in that radiation, it means when I match to the IR brane has to be doing something specific that matches that cosmology that you put in. And so when you put in this radiation term, well, you saw that there's a big bang from the UV brane point of view. So what's going on with the infrared brane? Well, it's big banging. It starts off very close to the UV brane, here, and as time evolves forward cosmologically, the IR brane starts running off into the bulk of the extra dimension. Now, if you look carefully at the metric here, what you'll find is that this lambda plus and lambda minus, these terms can work in such a way that this coefficient of the dt squared vanishes at some point in the bulk of the extra dimension. And so there's a near horizon, there's a horizon there, and the near horizon geometry is that of a Rindler horizon.
Now, this one, so this looks like a constraint where actually you're defining what is the y variable, because you can rewrite y in terms of a and t, right? And now it becomes standard symmetric in time.
Sorry, I can't write y in terms of a and t. Right? This is just the extra dimensional coordinate. I don't think I understand your question.
But according to this, it looks like a constraint between y coordinate a and time. So these are three variables that appear in this equation. I should be able to solve for y and rewrite everything without y.
Yeah, maybe we can discuss afterwards. No, this is a this is a function of y and t, and I can write down this function. I can solve the equations that fully determines exactly what this metric is. There's no constraint between this. Y is still a perfectly good coordinate. But okay, so there's a Rindler horizon in the bulk, and so what happens is, though, universally, the infrared brane starts off further from the UV brane than the Rindler horizon. So at early universe epochs, the UV brane observer sees off out there in the bulk a Rindler horizon and doesn't see the infrared brane at all. There's no infrared brane so far as the UV brane observer is concerned. And if you take this is looking at the simplest case of where I set the UV brane tuning to 0. You can go ahead and you can numerically solve these with relaxing that. This is just to pick a particular point. And what happens is, as time evolves, eventually the IR brane slows down, and eventually the Rindler horizon seems to universally catch up with the IR brane. So as the universe evolves, eventually the IR brane appears through the Rindler horizon, and the UV brane observer now sees the Higgs. Okay, and so now, this actually seems kind of interesting. It makes one think that maybe this radiation term is somehow related to the Unruh effect, which typically is a purely quantum mechanical effect for an accelerating observer. But here, it's just appearing by solving classical GR in an extra dimensional scenario. Okay.
What was special about t equals 0? What does that mean?
There's an integration constant T naught, and I set the Big Bang equal to T naught equal to 0. There's no physics in that. No. The T equals 0 is just where I chose to put the Big Bang, because that seemed like a good place to put T equals 0.
So in the Rindler scenario, the effective temperature is associated with the proper acceleration.
I would love to understand whether there's a temperature associated with this. I'm not sure if the UV brane has like a little, device, if the energy levels in the device will start to raise because there's a temperature bath. It's not clear whether there's a nice particle interpretation. Maybe there's some gravitational radiation that would equilibrate that little device with a finite temperature bath. But yeah, I don't know. It's an interesting question. Okay, just what did I have on this slide? This is just the summary of what I did on the past few slides. In this dark radiation from the RS brane world, this mistuning can require a Big Bang cosmology without any addition of matter anywhere. It's just the motion of two branes. And again, relativistic motion was crucial. This square root term is setting the speed limit, and near the Big Bang, basically everything's moving near the speed of light. And again, that radiation term appeared just as an integration constant. It's just sort of initial conditions for this brane universe. All right, good. So just generically now, so these are two examples that I've walked through. Have we classified all of the interesting geometries that might arise from brane worlds, but with particular focus on different instabilities that we've encountered as model builders over the last decades. You know, one interesting idea was this DGP gravity, model of gravity where gravity is modified at large distance scales. So an infrared modification of gravity that could have been exciting, but it turned out that it's plagued by all sorts of instabilities, ghosts. The Radion itself turns out to be a ghost here, the separation between two brane scenario in certain iterations of this DGP scenario. And what sort of got me onto it is different RS geometries that seem to be either very difficult to stabilize or perhaps unstabilizable in the sense of trying to have a Goldberger-Wise mechanism that stabilizes the interbrane separation. And so along these lines, okay, the system wants to be unstable, let's run with it, and I'd like to understand what are the cosmologies associated with these different classes of instabilities. Okay, we went through two. They have interesting phenomenology. What might we get if we are able to go further? Now, the lesson we might learn from the previous examples is that this relativistic motion is a crucial ingredient, and the resulting phenomenology is pretty intriguing. So let's talk just for a couple minutes about the Randall-Sundrum radion and how we know what we know so far about it. And by the radion right now, I mean the small fluctuations in the interbrane distance. When we study the radion, the way that we try to identify it is typically to expand the RS metric to lowest order in metric perturbations. You just go to linear order in the perturbations, and you go about and you try to solve Einstein's equations. And in the case of where you've stuck in all of those tunings exactly the way that you require to have a static solution, then you can identify a nice spectrum where there is a 4D massless graviton and a massless scalar field, which gains a mass if the radius is stabilized by something like the Goldberger-Wise mechanism, and an additional massive tower of Kaluza-Klein gravitons. Now this is at the linearized order, so this is very ill-suited to macroscopic motion of the branes. This encodes the lowest order derivative terms only. If there are higher derivative terms, as we expect there to be especially from the example that I just showed you, then you're not going to be able to track what the macroscopic motion of the brane might be in the presence of these types of instabilities that we're interested in. So linearized metric expansion doesn't do it. But as Adam as Adam had us discuss, when curvatures are small, the full EFT can describe large-scale motion of the branes. It can't describe very bunched up configurations, but large-scale macroscopic motion is on the table for the EFT, for the 5D gravitational EFT.
Sorry, Jay, just for me to understand, what is the perturbation parameter that is effective to the theory?
So it would be the terms in the action, I guess, corresponding to the curvature, both in the bulk, the usual Einstein-Hilbert term, and the induced curvature terms you might have on the branes. Yeah. So the terms that are appearing in the action. Yeah, that's right. Yep. So long as those curvatures are not very large compared to the localized M Planck, whatever M Planck those branes are feeling, then you're within sort of the safety grounds of the EFT of the theory. Right? All right. So now we know how to write down the action, at least for a single brane in space. If we have a thin codimension 1 brane in a space-time, we can parameterize the configuration of that brane in the space-time in which it's embedded by a set of functions x, and then the coordinates c parameterize where I am on the brane. So as a function of brane coordinates, where is that piece of brane located in the higher embedding space? And the action for the brane is just the integral over the tension times the square root of the induced metric on the brane, which is derived from those embedding functions. And you can choose coordinates, if it's a codimension 1 brane, such that this induced metric reduces just to eta mn plus these derivative terms acting only on one variable, one field phi, that parameterizes, so we basically choose the brane to be quasi-flat along most of the dimensions, and then the motions perpendicular to the brane are encoded by phi. And again, this square root is enforcing the causality limit on the classical motion of the brane, and there is a single massless degree of freedom. Again, if you expand this to lowest order in derivatives, there's no mass term here. Everything is derivatives. And so there's a massless mode, which you can interpret as a Goldstone boson of having spontaneously broken the space-time symmetries of the target space in which you've embedded the brane. Now, the key point is that the Radion action should be morally similar to this action that we just wrote down here. The Radion is an interbrane separation, and it should have aspects of its action that encode this constraint of causality in the bulk, as we saw in the dark radiation analysis that I presented earlier. Now, one thing maybe to mention in passing is that we are in part interested in these Randall-Sundrum type models because there are relationships between these models in anti-de Sitter space and 4D strongly coupled conformal field theories. And this duality between ADS and CFT relates the 5-dimensional radion to the dilaton of a spontaneously broken 4-dimensional conformal field theory. And there's a recipe for building actions which nonlinearly realize conformal symmetry in the case that it's spontaneously broken. And the recipe is the following. I write down a metric that is rescaled by a coordinate-dependent function tau, where tau is going to be related to the dilaton. And then the recipe is you just start building all the actions that are consistent with general covariance. So for example, the simplest thing you might write down is just a cosmological constant term plus the curvature plus the scalar curvature term, and then a bunch of higher derivative interactions that you can in principle add. But if I only do the simplest thing, you get out the following: d phi squared minus lambda phi 4, where lambda is a scale invariant quartic for the dilaton. So the simplest dilaton action has none of these higher derivative terms that would encode a speed limit for the branes. So the Radion is not at all the simplest realization of the dilaton. 5D causality requires a specific pattern of higher dimensional operators or higher derivative operators that are in principle related to constraints on interacting CFTs via the correspondence. And so this was recently explored a bit by the following authors, Bauman, Green, and Hartman earlier this year, where this has to do with the way that operators spread and mix under renormalization group flow or under time evolution. Okay, so there's something interesting about these higher derivative terms in terms of the relationship to CFT. All right, so now to the main thing that we are trying to do. How do we get this kind of how do we get at these higher derivative terms? How might we get a prescription by which we obtain these effective field theories that encode the constraints of the symmetries of the underlying space in which the branes are embedded? So we can do it for Nambu-Goto, the simplest brane action that we already wrote down just using geometry. And the idea is that the embedding of that D minus 1 dimensional brane breaks the Poincaré algebra down. That is, you break spontaneously a subset of the translations and rotations and boosts, okay? So when you put that brane in, it breaks the symmetries. And the low energy action should be described by a coset construction. There are some subtleties with spontaneously breaking space-time symmetries, of course. So if I have a d-dimensional Minkowski space and I slap a d minus 1 dimensional brane into that space-time, you get the following interesting thing. Well, clearly I've broken translations, right? The brane is there, but also I've broken the various rotations and boosts that have axes perpendicular to the brane. Okay, and so naively you would expect multiple Goldstone modes corresponding to this set of D broken generators. However, there's only one massless Goldstone in this picture. And there's a nice geometric picture of why the counting goes wrong, and it's the following. I want to make a lump on a brane, right? That's going to be the Goldstone mode, fluctuations of the brane. And so this lump on the brane is created by x mu dependent translations. And so to make a lump, I put in my e to the I pi's, and we make a lump, just like you would create a Goldstone excitation by acting on the vacuum state with e to the I pi. But the issue is that you can create that same lump by having an admixture of the unbroken translations and local Lorentz transformations. So these are the broken Lorentz generators. And so what you can do is you can make a lump, and then you can translate it around on the brane using the unbroken translation generators. So you shouldn't be that surprised that we got the counting wrong. There's two ways to make the same bump. And so in spontaneous breaking of space-time symmetries, the counting and spectrum of Goldstone modes is modified. Now, the reason I say spectrum is that this is not always a redundancy. When I break space-time symmetries, the identification of the Goldstones actually has crucially depends on the order parameter that is breaking the symmetry. For internal symmetries, it's always a scalar, yes? But if I break space-time symmetries, this brane could be spinning. That is, the brane could have an orientation, could have an orientation, there it is, that points to the left, yes? And so then these Lorentz generators, unlike the translations, would bend those spins relative to each other, and you'd have sort of like a spin-on, a spin wave kind of thing that would propagate across the brane.
Funny the name of the Jill.
All right. So now, now that we've identified the possibilities of these redundancies, we can start turning the crank and start to build phenomenological Lagrangians using the standard coset prescription. The idea is that the low energy theory nonlinearly realizes the broken symmetries via the Goldstones, so we can build a space-time dependent group element G in the following way from the Goldstone bosons multiplied by the broken generators, and now you start to search for something that transforms nicely under the original symmetries of the theory, and the Maurer-Cartan form, which is this mathematical object, has precisely those properties. The Maurer-Cartan form sort of lives on the algebra.
That's called the Maurer-Cartan form? Okay.
Yep. And so it lives in the algebra, and so it has components along both the broken and unbroken directions in the coset space. So the broken part transforms linearly, and so you can take this guy here and you can just trace and contract it any way you like, so long as you've sucked up all the indices. You've got a nice phenomenological Lagrangian encoding, for example, the kinetic term for the pi's, which will live here, as I stitch together those guys with each other, okay? The unbroken part transforms nonlinearly, like a gauge field, and so you could use that to couple Nambu-Goldstone bosons, these pi's, to light matter fields that might be in your low energy effective theory. So what about CCWZ and the brane? Okay, well now I got to write down the most general element that encodes all of those different broken generators, but you have to include both the broken and unbroken translations, because to make a lump, using the Lorentz generators, you also needed to be able to move the lump around once you created it near the origin. Yeah? And so you've got to include those guys there, and so your Moore-Cartan form involves both of the broken and unbroken generators. Okay, and there's some details here, and I'm low on time, but the idea is that if I set to 0, this component here, that corresponds to removing that redundancy between the making a lump with the translations and making a lump with the boosts. So essentially, it looks like there are many degrees of freedom here, but it is setting this to 0 eliminates some of those degrees of freedom, and once you do that, that leaves only one Goldstone boson for the brane, that is the transverse motion. These are referred to as the inverse Higgs constraints, and they are a choice that corresponds to a choice of the order parameter that you chose to break the Lorentz symmetries. So if it's a spinning brane, you wouldn't be able to do this. These would actually encode the massive spin-on modes that still fit under the header of Goldstones. They're just gapped Goldstone bosons. These are very familiar from condensed matter systems. Okay. And so if you turn the crank on this, voila, you get out the Nambu-Goto action. There's a Vielbein type object that appears here, and if I trace and contract that guy, the simplest way to trace and contract it is to just build a little volume element out of it, and you can twist and pull on this, and you find out that it gives you precisely the square root of the determinant of the induced metric, where those y's, which before were arbitrary functions, are actually the embedding functions of the brane. Okay? And again, like you mentioned earlier, it also, using these other terms, gives you a prescription for adding things like extrinsic curvature and coupling of matter fields that you might put on the brane to this Goldstone boson. And it's all defined by the CCWZ prescription. So now the idea is we'd really like to see this applied to realistic brane world scenarios and RS-type models. We know that the Radion has got to be some analog of this, but with the caveat that there's a lot more going on in an RS brane world. That is that there's dynamical gravity in the picture. And so just a sketch of what it is that we're trying to do is that because the Radion is part of gravity, you can't get just the Radion without trying to get everything else along with it. That is, the graviton and the KK gravitons and all this are actually Goldstone bosons of some sort of symmetry breaking pattern. And there is a formalism explored somewhat. It's an older formalism than this, but it's been explored recently in the context of Galileons and massive gravity by these folks here. And the idea is that you can reduce or write down the full set of diffeomorphisms, which is a continuous, set of continuous symmetries, in terms of an infinite number of space-time dependent global symmetries. And then you say that all of these global symmetries are spontaneously broken, and the spin connection, which has like the gauge field for gravity, is the thing that transforms non-linearly under all these. And there's a whole pile of inverse Higgs constraints that you've got to impose, but at the end of the day, you actually reproduce Einstein-Hilbert gravity or massive gravity, et cetera, depending on which of these things that you decide to break. And so our first effort to try to get to the Radion is trying to do just 5D Kaluza-Klein theory. So just take gravity compactified on a circle and see if we can get at least that. And we actually have, even though this is a holy mess and it's only one tiny subset of all the stuff that you get, if you stare into this abyss of stuff, you see something that is going to end up being the Vielbein, that when you write down the invariant volume element involves something that corresponds to dilatations of the extra dimension, which is living right here, and also a gauge field. So 5D Kaluza-Klein theory has a massless dilaton, it has a massless gauge field along with a massless graviton. And it's looking like it's getting it for us. It has those terms before implying inverse Higgs constraints. B and A are indices that live in the tangent space manifolds. They're the Lorentz indices living on top of the top index of the Vielbein. So the mu's are space-time indices, and the A's and B's are the Lorentz indices. Okay, and out of this mess, it looks like you're starting to get something that, that looks like it contains the dilaton and the gauge field. And when the dust settles, I'll be very surprised if this answer in the end isn't the analog of the Dirac-Born-Infeld action, where you get not just the determinant of the metric, but also something that involves the gauge fields fitting under the square root, where here we're getting it purely from cosets, and we haven't talked directly about geometry at all. It's just sort of an algebraic realization of the same action. And then, of course, next, we'd love to take this and apply it to the Radion. So I'm giving you a picture of where we're trying to go with this in our motivations. And I'll conclude. And yeah, brane worlds are fascinating for cosmology. As I said in the beginning, you get these interesting things where you get matter or radiation type behavior, aka for free, sort of for free. The idea is that we want to bring the tools of CCWZ to go beyond the linear order so that we might take the tools of CCWZ, get the all orders in derivatives Radion interaction, and maybe apply this formalism to these curious instabilities that we've encountered over the last decade. So hopefully our dark universe, at least by us, is one animal perhaps in this sort of zoo of brane worlds. Thank you.
Questions for Jay? I have a simple question. So you're talking about spontaneous breaking of this of Lorentz symmetry in the direction of the brane, right?
Mm-hmm.
But the location of the existence of the brane doesn't already break Lorentz invariance. Just the fact that there is an IR brane, that the space explicit breaking, just because. Maybe I'm just being stupid.
So I guess what I might try to do is.
Just you being stupid.
Yeah, that. For that you have an answer, I know.
So.
Break? No, doesn't break explicitly.
No, yes, it's a good question.
I think you can maybe view it in the following way. And so this is one. I'm not sure if this ends up being the best way to see it, but I think when you have these brane worlds that have an extent in an extra dimension, that I can think about embedding that whole fat brane kind of into a larger target space. And so here's my fat brane, and I've still only spontaneously broken the translations perpendicular to the brane once. Even though I've got all this stuff there, and I can spontaneously break symmetries as many times as I want, but so far as the Goldstone connection, there's still only going to be one Goldstone boson. So I think that's roughly my guess of the answer to your question. Yeah.
More questions for Jay? Yes, just 1 second.
I was wondering, when we have these branes, what constrains the matter to stay on the brane?
Well, so the solutions to the equations of motion. So if you wanted to add some matter to this picture, you might start by adding something in the bulk, right? Letting it go free, so to speak. But then you might do something like add a mass term for the field in the extra dimension. And so, for example, if you add a fermion mass term and you follow through the equations of motion, and you've got sort of a compact space like this, the fermions exponentially localize to either the left brane or the right brane according to their mass. So the fermion wave function will fall off as e to the minus my as you move away from the brane. And so what's keeping the fermion from running away from the brane? It's its own mass term. And so it just arises from solutions to the 5D equations of motion and identifying the lowest lying modes of the whole spectrum that you'll get out of this and seeing that you can localize them.
So it should be mostly actually quantum mechanical effects, because the solutions...
Well, these are just classical solutions that you would then go ahead and quantize. So you solve the classical equations of motion in the bulk, and then like you normally do, you promote them to operators, and this guy will create the lowest lying excitation in the spectrum.
Okay.
So you had some comment about counting on Goldstone modes. Could you repeat that because it went too fast for me, and I want to understand well. Space-time. Exactly, the space-time.
Right. So when you break space-time symmetries, there's more than one way to create the same deformation of the system that you try to do by acting with one of the broken generators. So another famous example is that of conformal symmetry, where you have the dilatations and then you have the special conformal transformations. And the configurations that you'd like to create, say, with the dilatation operator can also be created with the special conformal transformations by performing a special conformal transformation near where you want to create your lump, and then you can use the unbroken translations to move that lump around. And so you can do the same thing with local dilatations as you can do with local conformal transformations. And so the idea is that there's a redundancy. The Goldstone is the lump, and if I can make that lump in more than one way, then there's sort of like a gauge fixing that you might do in the coset space that removes that redundancy. But you have to be careful, again, because if the order parameter is not a scalar, for a scalar brane, you just remove it, you fix it away, but you can't do that if the order parameter carries its own Lorentz quantum numbers beyond scalar, right? So if the brane is spinning, for example, then yeah. So you have to, it's not like internal symmetries. You have to say something about what the UV physics is in order to properly understand the spectrum of Goldstone bosons. And some of them may be massive Goldstones.
Okay, so if there are no further questions for Jay, let's thank him again for this nice.
Thank you.
So there's a coffee break. We're running late, so let's be back at 20 past 11. Okay. Thank you, Jay. So I'm not claiming I understood everything.